Hello everyone. So today we're going to continue on 13.2. So the last thing we did, we stated theorem 13.2.1, which told us that whenever we have a square matrix, we can always find this thing called matrix exponential by forming this infinite matrix series. And we'll always be able to have it converge to something. And obviously, the question that we go try to figure out is how do I find out what it converges to? And no, we're not going to stay around trying to add a whole bunch of matrices together forever to try to figure out what it is. That's not practical. So we're going to have to eventually talk about different ways to come up with this matrix exponential. But before we do that, theorem 13.2.1 also stated it has these three properties. It doesn't have a lot of other properties that we can state, but these are the three properties that are more relevant to what we're going to be doing. That's the reason why we state them. And the first one is that when you multiply two matrix exponential together with the same matrix A, you can simply combine them together by adding them. And the inverse of a matrix exponential is simply just raise it to negative exponents. And most important of all is that when we take the derivative of that with respect to the variable t, it's simply just equal to the matrix multiplied by the matrix exponential. And that is actually extremely important for what we need, because that would allow us to use it to solve system of differential equation. But before we get to that, let's try to do proof. So I do want to go over the proof with you just so that you see how this thing works. So some of these proof hard to follow, so make sure you try to keep up, okay? So the first property that I want to prove is this one. Is e to ta, e to sa equal to e to t plus sa. I'm not going to prove the backward because it's just basically me switching letters. So I'm just going to simply show this. Okay, so now how do I actually prove this? Well, I see no other way to prove it, but go ahead and give it a try and just brute force it and see, hopefully get to work. So I'm going to go ahead and define this. So I'm going to go ahead and let e to ta equal to summation j from 0 to infinity t to the j over j factorial a to the j. So basically just mean I plus t times matrix A plus t squared over 2 factorial matrix A squared plus t to the third over 3 factorial A to the third plus t to the fourth over 4 factorial over A to the fourth plus dot dot dot. I do want to write out the first 4 terms because of what I probably want to do next. And we will go ahead and do the same thing with e to sa, which would actually equal to summation j from 0 to infinity s to the j power over j factorial a to j. So that will be I plus sa plus s squared over 2 factorial a squared plus s to the third over 3 factorial a to the third plus s to the fourth over 4 factorial a to the fourth plus dot dot dot. So now come the big problem. Is I'm going to try to multiply these two things together. Well, as you can see, both of them are infinite series. So what will happen when I try to multiply them together? Well, let's find out. So e to ta times e to sa would basically meaning I'm taking these two infinite sum and multiply them together. So clearly, it's not going to be easy to try to multiply two infinite sum together into one thing, and because the infinite term to multiply, so how are we going to find out what this is equal to? Well, once again, just like what we did before, I don't have to multiply everything out, but I just need to multiply enough things out to hopefully, in a way, allow me to kind of come up with an idea as to what this would be. So meaning that what I'm going to try to do is try to mathematically show what this sum is going to be and argue that this should be the sum instead of trying to add it up forever. So how am I going to do that? Well, how about we just simply multiply out and see. So what I'm going to do is, this is what I'm going to do. I'm basically going to take this whole thing and then multiply to each one of these. And so on. And so forth. And hopefully, after I do that, I will be able to come up with some kind of pattern that I can use to help me out. So I'm going to go and do that. I'm going to take this I plus ta plus t squared over 2 factorial a squared plus blah, 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 and multiply by I. So when I multiply by I, it's technically just stays the same. So therefore, just be I plus ta plus t squared over 2 factorial a squared plus t to the third over 3 factorial a to the third plus t to the fourth over 4 factorial a to the fourth plus dot dot dot. So that will be my first product. And I'm going to add. Now my second multiplication will be taking this whole thing and multiply s times a. So when I do that, I do want to line up my terms properly. So if I take I times sa, I get sa. If I get ta times sa, I get tsa squared. Okay, everyone hopefully see what I'm doing. Is I'm placing I times sa, ta times sa, and now t squared over 2 factorial a squared times sa would now become t squared s over 2 factorial a to the third. Notice that everything shifts over one term because I'm taking this entire first summation and multiply sa because of the a involved. Every power just shifts over. So the next one I'm going to do is it would be t to the third s over 3 factorial a to the fourth plus dot dot dot. And I'm not going to write out the rest of the term because I won't have enough to combine them anyway. So that's taking the whole entire first matrix series and multiply by the second term in the second matrix series. Now we'll go to the third one. So third one, if I take I times s squared over 2 factorial a squared, that becomes s squared over 2 factorial a squared plus, and I'm going to take ta times s squared over 2 factorial a squared, that becomes ts squared over 2 factorial a to the third plus the next term would be t squared s squared over 4 over 3 factorial. Let's see. The third term multiplied by the third term. So it's 2 factorial times 2 factorial. A to the fourth plus dot dot dot. All right, and maybe we'll do one more and see how this one goes. So let's see if we can do one more. Plus, and now what I'm going to do is I'm going to take all of these and multiply by the fourth term. So the first is I times 3 s to the third over 3 factorial. A to the third plus the second term times the third term, fourth term here would be t s to the third over 3 factorial a to the fourth plus dot dot dot, and then this sum continue on forever and ever and ever and ever. So I think we have enough to try to figure out what's going on here. So let's see if we can kind of come up with an idea as to what this is. So notice that I purposely kind of write out each multiplication and line up the proper term because these are the term, these are terms that's going to combine together. And I want to see if I combine them together, what would happen. Okay, this one I'm going to have to actually write one more term for this. because otherwise we can't combine them properly. So we'll just do one more term. So that will be this times the fourth term. So it will be s to the fourth over 4 factorial, a to the fourth, plus dot dot dot. So now I can properly box in. Yep, because the next sum would not have a to the fourth term anymore. So now the question is, what are these combined to? Well, let's find out. So therefore, that would mean that this is equal to I plus TA plus SA plus t squared over 2 factorial a squared plus TSA squared plus s squared over 2 factorial a squared plus t to the third over 3 factorial a to the third plus t squared s over 2 factorial a to the third plus t s squared over 2 factorial a to the third plus s to the third over 3 factorial a to the third plus, you know what, I'm just going to leave out the last set. That's just way too much writing. And as we all know, mathematicians hate to write. So that doesn't seem like anything that we can work with, but actually it does. Notice the following. I'm going to go and factor out the a. Okay. Now for this one right here, I'm actually going to factor out 1 over 2 factorial, and I actually wind up having this. Oh, actually, I'm going to pull out the a too. And for the third one, I'm going to pull out 1 over 3 factorial, and also the a to the third, of course. Then this will come out to be this. Yeah, I don't like my plus sign. Sometimes I have a little hook because that looks kind of like T, so I'm trying to fix that. And the interesting thing about it is that these right here, that actually is T plus S square. And this one right here actually come out to be T plus S to the third. So therefore, imply that this summation should come out to be this. And that is basically the summation that we define e to the TA with, except that we replace t or s, depending on which one you look at, with t plus s. So therefore, this would actually sum up to be this right here, which is equal to e to the TA times e to the SA, as what we require to prove. So that's actually very neat, that how all these things actually work out perfectly. Now, to prove property number 2, wait, did I use 2 or B? 2. So to prove property number 2 is actually pretty simple. 2 simply have to prove that e to negative TA times e to TA would equal to the identity matrix. So the easiest way to do that is to simply replace our previous proof with negative t in place of s. So therefore, I can say this is basically what happened. E to t, a negative ta, e to ta would basically equal to e to negative t plus t of a. And essentially what does that mean is that basically we're forming this summation right here. And as you can see, this turned out to be 0, that turned out to be 0, that turned out to be 0. So essentially what we have is just I times whole bunch of 0 matrix afterward, which clearly come out to be I. Which also interesting thing to note is that means that e to the 0t is equal to I, which is equal to negative AT times e to the negative TA times e to TA. Which kind of makes sense, because if you have e to 0 times t, you basically have e to the 0 matrix. And that basically just means you adding a whole bunch of 0 matrix power together. And therefore you just have the identity matrix in the beginning. So that one is rather easy to prove. So now let's move on to probably the most important one that we have to prove, and that's property number 3, the derivative. So this is extremely important because if with this property, we can now actually try to use the fact that because it's e to matrix exponential is its own derivative, to use it to solve differential equation of the form d vector x over dt equal to a vector x. So let's see how that works. Okay, so once again, we're going to say that e to ta is equal to I plus ta plus t squared over 2 factorial a squared plus t to the third over, there you go again, 3 factorial a to the third plus dot dot dot. So that's how our e to ta work. It's defined the same way as this. And maybe I also go write out as a summation. So that's equal to summation j from 0 to infinity, t to the j over j factorial, a to the j. Now, what if I want to take the derivative of this thing? Well, let's do it. I'm going to try to take the derivative with respect to t of e to ta. So what would happen to this thing right here? So let's try to take the derivative of e to ta and find out what happens. So remember here, t is the variable. A is technically speaking a constant matrix. So if I take the derivative of I, that has no t in it. So that just go away. Or you can think of it as to become the 0 matrix. Not 0. 0 matrix. Okay? Next, what happened when I take the derivative of ta with respect to t? Well, that just gives me the matrix A. And what happens if I take t squared over 2 factorial a squared? So that becomes 2t over 2 factorial a squared. Notice a squared is a constant because I have no t in it. Plus 3t over 3 factorial a to the third plus dot dot dot. And I'll show you what happened to the summation afterward. But let's try to figure out what happened without the summation first. And then when I show you the summation, it'll probably make more sense. Okay? So notice that now what I have is this thing right here. So several things happen. Number one, the 2 would cancel with the 2 factorial. The 3 would cancel with 3 factorial and become 2 factorial. And if there's a next term, okay, maybe I should write out a next term just so for you to see. So the 4 and the 4 factorial cancel out to a 3 factorial, and so on and so forth. And notice that now once I do that, there's now a mismatch between the factorial, the exponent for t, with the exponent for a. Oh, I forgot a square here. For the power for a. But lucky for us, the first term dropped out to be 0, and now I have a common factor that I can factor out. So now if I pull out an a from all of them, I will now have I plus ta plus t squared over 2 factorial a squared plus t to the third over 3 factorial a to the third plus dot dot dot. Notice that this summation is exactly the same as this summation, except that it's kind of one term over with an a in front. So therefore, this would come out to be a e to the ta, exactly as what we want to prove. Now, I also work out with the summation also, if you want to think about what happened to summation. So if I do take the derivative of this summation right here, notice that doesn't change the summation, because summation is just adding a whole bunch of things together. And the t to the j become j t to the j minus 1 over j factorial a to the j. And so what happened is exactly what happened right here. The j and the j factorial cancel to j minus 1 factorial. And also, interesting thing about it is that the derivative, meaning the first term go away and become 0. Or become the 0 matrix. So therefore, I can now discount the 0 term and start with the 1, the first term. And now this would basically just form this summation. T to the j minus 1 over j minus 1 factorial a to the j, which what we're going to do is we'll separate the a to j into a to j minus 1 with an a in front. And this basically formed this summation right here. And I know what you're probably thinking. You're thinking like, well, but this one's to j minus 1 power. But it doesn't matter to j minus 1 power because it still go on to infinity. That's the key. So that's why this would still end up being a e to the t a, which matches our formula right there. So that's pretty crazy that it actually have the same exact property as our exponential function e to the x. And which is exactly what we need, because if we want to use this to solve a system of differential equation, we need that to be true. So now let's talk about how do we take advantage of this. Well, imagine the following. What we want to do now is the following. How to use this to solve systems. And that's probably the last thing we're going to talk about in today's video, so that hopefully we can make it before 30 minutes. So imagine that we are given a system d vector x over dt equal to a vector x with, let's say, initial condition. What we want to do is to show that we can use matrix exponential to form the solution to this differential equation, to this system of differential equations. So what we want to do is this. We want to show that vector x of t equal to e to t a vector x sub 0 is the solution. So not a general solution, but specific to the initial condition, is the solution to this initial value problem. So how do I do that? So actually pretty simple. In order to show that vector x of t equal to e to ta vector x sub 0 is the solution to this initial value problem, all I really have to do is to show that it would satisfy the differential equation and it would satisfy the initial condition. So this is what we need to do. To do that, we need to show two things. So which two things? Number one, vector x of t equal to e to t a vector x sub 0 satisfies the differential equations d vector x over dt equal to a vector x. And number two, we also need to know that this expression satisfies the initial condition. So nothing to it, but give it a try. So go let vector x of t equal to e to t a vector x sub 0. Then I can now do d vector x over dt. That would mean taking the derivative of e to t a x sub 0. So remember, vector x sub 0 is a constant vector. So I'm going to move that out of the derivative. But here's the important part. Because matrix multiplication is not commutative, I have to move it out in the same order as the multiplication as indicated. So I have to move it out to the back. I cannot put it in front because that would screw up the matrix multiplication. And now, since we already established that when we take the derivative of e to ta, I just get a e to ta. So therefore, it becomes a e to ta vector x sub 0. Now, let's see what a times vector x would be. So that just becomes a multiplied by e to ta vector x sub 0, which is a e to ta vector x sub 0, which matches what we have right there. Therefore, so that showed the first thing we need to show. The vector x of t equal to e to ta vector x sub 0 will satisfy our differential equation. Now let's try to do the second one. Let's say I take this, and now I'm going to plug in 0 to see what happened. So that just equal to e to 0a vector x sub 0, which we know that e to 0a, as we already show right here in this property, that just equal to I. So therefore, that just becomes I times vector x sub 0. And we know that anything multiplied by the identity matrix stays the same. So therefore, tell me that that just equal to x sub 0. That shows that our equation will satisfy our initial condition also. And therefore, showing that it will be a solution to our system of differential equation. And I know some of you probably thinking like, that's kind of weird, but it's not. Remember, a system of differential equation often have infinite solution. And then once you have the infinite solution, you can then plug in x sub 0 to form the solution that satisfies the initial condition. So it's just a matter of using some way to represent that solution. So, and this solution can be represented using different method in different form, but they all meant the same thing. Okay, that's the tricky part, is that your answer is not like unique looking. It can look differently, like in parametric representation, where you have the different parametric representation represent the same geometrical object. So here's the same exact thing right here, which is where students get confused. Because like, oh my god, that can look so many different things. Yeah, it can. Now, it's 29 minutes, so I'm going to just say one more thing, and that would be it for today's video. What if your initial condition is not at t equal to 0? So for initial value problem, in this case, like this, where t sub 0 may not be equal to 0, then the solution is simple. Then the solution is simply this. We just translate our solution. So that our solution would line up at t sub 0. Plain and simple. All right, unfortunately, that's all the time I got for today. So we're going to stop right here and we'll continue some more on the next video. All right, talk to you guys later. Bye-bye.